All right, we're back. We are GAME 2005. That's game physics in the fall 2017 semester here at George Brown College. And we are week 3. Guys, I can't speak over you guys, and I can hear you very clearly. Part 1 of our broadcast. Today, we're still talking about derivatives, specifically the chain rule. That's the portion we left out last time, as well as integrals. Now, I did, for people who were in sections or the lab 2 and 3 or whatever it is on the Thursday, I did show you kind of an a overview of what I'm doing. I will be sharing that with the section 1. Today, after this class, we have our lab. But today I want to talk about chain rule very briefly and then move into integration. All right, so by the way, if you're not in, for whatever reasons, if you're not in game physics, game 2005 game physics, then you're in the wrong class. Please don't stay. It's gonna be a waste of time for you. We're talking about, again, the last part of derivatives. Just one more thing about derivatives, which is the chain rule and integrals today, like we said. And we're gonna handle a few things today. We're gonna talk about the chain rule. Like I said, there's 2 types of integrals I want you to think about and know. One of them is called definite integrals, and the other type is indefinite integrals. Again, just as a reminder, when we talk math and physics in this class, remember that we're just scratching the surface just to hit the highlights of the stuff you need for game physics and for stuff that you're going to do with game, right? So there may be some things that I don't cover that you would normally get in a math course, but that's because this isn't just a math course. It's kind of a combined math and physics kind of course for game. All right, so we got this idea of the chain rule, and we didn't even talk about this, but let's say we have this function x to the 7. That's easy to differentiate. We just take the 7 down in front of the x, like we learned last time, and we subtract 1 from the exponent, which is what leaves us with 6. So 7x to the 6. What is that rule called from a differentiation perspective? Anyone can connect to power rule? Power rule it is. That's the one, right? But what about this one? What about this second equation here that I'm showing? 5x squared plus 2 all to the 7. How do you figure that? I mean, if it was to the 2, maybe you kind of can multiply everything together and, you know, do the differentiation that way. But this is like you have a function inside of another function. And I kind of talked about this during lab as a preview. Right? So imagine I want to do the stuff on the inside somehow, deal with the stuff on the inside, and also deal with the outer function, right? Which I have to differentiate both, right? Now, it would be incorrect to think that I would just do 7, I'll pass the 7 down in front of the brackets, and then take 1 away from the exponent, so it would be 7 minus 1, so that would be 6. And then you'd have your inner terms, 5x squared plus 2, and that would be it, right? Now, if you can imagine that the stuff in the inner part of the equation is just a variable, let's just call it z for now, right? If it was z to the 7, if we can imagine that whole part inside is z, and if it's z to the 7, then it would be 7z to the 6, right? That would be differentiating. But we do have another value inside of the function. Z is actually a function itself, right? It just doesn't. It's not just the z to 7. So we have a function inside of there. And so the rule is, and this is very simple, you need to differentiate the stuff that's in the middle, take it out, and multiply it by the derivative of the first function. So for example, here's our general form down here. Let me just make this a little larger so you can see. You can see that the derivative of f of x is the derivative of f, that's the outer function, right? Multiplied by the derivative of g of x, let's say the inner function. Okay, that should be the answer. So for example, this one would equate to, who can help me out with this one? What would be the final? What's the final version that I'm looking for? I remember we talked about final versions in lab, right? So what would it be? Is that the final? Is that your final? Is that your final answer? No.
70x plus 2.
No.
To the 6th.
Close. That's getting there. So let's do this. Let's do what it says here in the general form. So I need to take the derivative of the outer term. So that's 7 on the outside. And inside would be 5x squared plus 2 to the 6. And then you multiply that by the second one, which would be 10x, right? 2 would disappear because that is a constant, and derivative of a constant is 0, right? So it would be this, so 7, 5x squared plus 2 to the 6 times 10x. And that would be your derivative. Does everyone see that? So the chain rule, if you haven't seen it, I'm going to write it in a second. If you haven't seen it before, right? If you've never seen this stuff, you're like, wait a minute, it doesn't make any sense. So let me write it down for you so you can see the difference, right? So I'm going to try my best here with PowerPoint, right? So the answer would be, I'm just going to use the equation. So in PowerPoint, if you're going to write your assignment, by the way, which I'm going to give you, you can certainly, Word and PowerPoint both have the ability to insert an equation. So this is how I would do it. I would look at, you look at their symbols. There's two. There's equation and symbol. Let's do equation, right? And what it allows you to do is do some funky symbols for yourself. Instead of writing slash for divide and so on, this is kind of really cool. So what you can do here is in the equation, right, I can change the shape of what I'm putting in here. So again, what I want to do is start typing. So 5, right? And I want to put this to the 7 like this, because that's the first thing. It wouldn't be 5. It actually would be 7, right? So 7. And then I want to put this whole thing to the 7. So I'm going to multiply it by this. This is how I'm going to write it, just for those people who know. So you see it gives you some spaces. So this would be the brackets, right? So it's 5. And then I would multiply this x squared. I would do the same thing. Just to show you how I compose this thing, x to the 2. I'll keep the same function, right? Plus 2, right? And that's all to the 6, right? Because that's the first part. So this is the first part of the equation, right? Now, if you notice down here, I got to multiply it by g prime at x. G prime is the stuff in the inside. So there's f. We kind of say f at g at x. That's what we say. So find the derivative of f of g at x, right? You can see that there's 2. Right? And then we're going to go to the next part. So we're going to say multiplied by, the derivative of the inside, which is just 10x. And that's your answer, right? Because the derivative of the inside is 2 times 5 is 10. 2 minus 1 is 1. And any x to the 1 is just x. So therefore, it's 10x. Does everyone see that? Right, the 2 is a constant, so it disappears, and that's what you get as the final derivative. Anyone not see that, please put up your hand, right? I'll explain it again. You don't understand that? Okay, let's go over this again. So I've got this part that's original, and normally what we would do is we would take the 7, put it in front of this term. Imagine if this whole thing, if you can imagine, this whole thing here, imagine if this was this part here with the brackets. I can't really highlight it because I'm in equation mode, but this whole thing right here, from 5x squared plus 2 in the brackets, let's imagine that is a z, some variable, right? If it was z to the 7, how would you differentiate? It would be 7 passed down to the front of the z, so 7z to the 6, right? Which is what I've just done here. Imagine that this is still the z, this part here. I've done 7, whatever this is, z to the 6. And that would be okay if it was just a z, but unfortunately inside we have more information that the inside is actually another equation. And so what we need to do is differentiate the inner equation and multiply it by this as well. So that's how we do it. So we take 2 times 5 is 10x, and we drag it out and multiply it by the whole, this term here by this. And that is your final derivative of this equation. Okay, you see that now? This is the derivative using the chain rule. So again, we've learned how many rules? We've learned the power rule. We've learned the subtraction and addition rule for derivatives. We've learned the product rule, right? Derivative of the first times the second plus the derivative of the second times the first. That's the product rule. And then we've learned the quotient rule last week, which is the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, right? That's the quotient rule, right? And now we've learned the chain rule, which is you take the derivative of the outside and multiply it by the derivative of the inside. Yes? Nope, we're going to give you some other options. Let's just say there's two equations or two functions, and one is inside the other. So this will be the answer to this one, right? And let's get some other possibilities. Here's another way to look at it. Imagine if you have this g of x function. So there's the outer component, the outer function f, and the inner function g. This is another way. And by the way, you'll see this online a lot too when we talk about chain rule, right? And what you want to take is the derivative of g of x, right? And we want to drag it out. Normally, notice what we say is we call the inner function u. Okay, it's just another variable that we're using. Okay, so it's like we're saying it's like f of u. And when I'm not saying fu, by the way, right? I'm saying it's f of u, right? And so if I do this, by the way, this is like right up online if you look at this, right? So again, like I'm picturing the inner equation, whatever it is a single variable, right? That's the first part. The first part is understanding that you want to look at the second equation as an inner variable, right? Or another variable. And then if you look at it, what you want to do is do something like this. Y prime then would be f prime at u times u prime, which if u prime was the derivative of the inside, that's what we're doing. It's another way of writing it, okay? So you may see it in this form as well, yes.
So that is exactly the same equation.
Exactly the same. I'm just using the chain rule, and I'm just making it so that you can see that I've only, swapped out the inner equation for u, whatever u is, right? And normally, if we only had u, right, and if we didn't have we have an idea what u is, we could take the derivative of u. Let's go further than that. What if it wasn't really an x? Could we still apply this same chain rule? Think about it. If it was f of x, I want to find the derivative of x. What's the derivative of x? 1, right? And then if I'm finding the derivative of x, which is 1, and I multiply it by the derivative of x, which is also 1, right? Then it's still 1, right? So it kind of works out if you think about it. If f of x, if I say f prime at x, if y prime is equal to f prime at x times x prime, at the end of the day, you're multiplying 1 by 1 because x by itself is 1 and x prime is still 1, and so you get 1. So this kind of works if you look at it in terms of any number, any kind of equation you plug in there, right, where u is equal to an equation, not one single variable, right? Where can this help us, and why am I even telling you about this ugly thing, right? Because this is where people get confused. If you haven't been confused by the first half, by last couple weeks of class, this is one place where you get confused, right? Because people have some more challenging equations. Let's take some examples of this idea, right? Make this a little bigger. So let's, for example, say that y then is equal to f at g at x. That's how we say it. That's our syntax when we talk about it. We have an equation on the outside, and we have an equation on the inside. So y is f at g at x, right? And we want to find y prime. So we want to define a couple things. Now, in this case, they're using u. It doesn't matter u or v, right? Where u represents g of x. Here's g of x. And y, I love this, is equal to f at u, right? Woo-hoo, right? F at u, right? So here's the equation. Y is equal to 1 over x plus 1. Then u, g of x, the inner equation, is x plus 1. And y, the outer equation, is 1 over u. And what's 1 over anything? How do you find the integral of 1 over something? If you think about it, 1 over u is equal to what? U to the minus, right? So if you think of it that way, you do the outside first, find the integral for it, the derivative for it, and then you take that u, in this particular case, x plus 1, and you multiply it by 1. Because x, the derivative of x is 1, so at the outer term you get whatever it is, 1 over x plus 1, the derivative of that, times 1 in this particular case, because u is equates to 1, right? Let's do something that's more a little easier. And these are some practice to get your mind wrapped around it. You see that there's some more complex forms. So here's another one, sine of 2x, right? You want to find the derivative of this. Well, there's two functions here, right? You've got u, which is 2x, And you've got y, which is the sine of u. So the outer equation is the sine of u. The inner equation is 2x. Let's differentiate the outer equation. It would be cos of u, right? Cos of u, which means it would be cos of 2x, multiplied by the derivative of 2x, which would be 2, right? You ever see that? Everyone see that? And you can, I'm going to go over the other ones in lab a little bit more carefully. It's going to take a little bit more explaining to do. But this is an idea of one way of thinking about that equation. The chain rule, if you think about, if you assign, we can say let u be equal to x plus 1. We're making a variable, right? We're assigning a variable u to the equation. And this is just to simplify your thinking. Okay, let's think about this one. What approach would you use for this one? What's the outer equation and what's the inner equation, and what would you need to do here? All right, if you saw this thing. Again, I'm going to cover this in detail at lab, but can anyone come up with a way of doing things here for the first one? Yes.
4x squared plus 3x minus 1 whole power half. We can do that.
Okay, so let's think about the outer one. What's the outer equation? The square root, right? The square root is the outer equation, right?
So like W to the 1/2 or something.
Okay, let's say u to the 1/2 or whatever, right? Or we'll say w. We can use w to the 1/2. Doesn't matter. And then the inner equation is 4x squared plus 3x minus 1. That was, let's assign that to u. So let u equals to 4x squared plus 3x minus 1. So what is the derivative of this? Well, what is something to the 1/2 or the square root of something? As long as the square root of something inside is not equal to a negative number, we have to put that in there as well, right? Anything to the half is, what's the answer to that? How do I take the derivative of that? I take the half, right? I pass it into the front, so it's whatever it is times 1/2, right? And whatever that equation is, so let's say w times 1/2, right? And then, or we'll say u times 1/2, and then to the negative 1/2, because we're subtracting 1 from it, right? So it's to the negative 1/2. That's the derivative of the outer equation, right? So 1/2 to the u to the negative 1/2, where u is equal to 4x squared plus 3x minus 1. And then we take the derivative of the inner equation, which would be what? Come on, this is just practice from last week. Anybody? 8x plus 3. And you multiply that first derivative by this other derivative, which is 8x plus 3. Does everyone see that? Right? So again, you take the derivative of the outer and multiply it by the derivative of the inner. That's how I remember it. Okay? Same thing here. Now this is a little bit somewhat the same here. So we have, let's say let u equal to sine x minus 5x to the 3. And we're going to say that if you want to find the derivative of u to the 6, right? If you can think about this in your head. By the way, if you can't visualize this at lab, I will actually put let u is equal to this and u to the 6, and we'll try and do it together. But picture this in your mind when you first look at this. If you can, this is the first part, is trying to understand the concept here. So I'm going to take 6 u to the 5. That's the first part, right? Where let u equal to sine x minus 5x to the 3, right? And now I'm going to take the inner, plus cos x, right? This one here has one more thing you have to do. You can treat cos x separately because it has nothing to do with the chain rule, right? So you process that right away. It would be minus sine x, because that's what cos x is, right? Okay, and you put that aside. You put that way on the side. But you still haven't finished the first part, right? And then you multiply the first term, which is u to the 6, multiplied by the inner part, what u is, which is just cos x minus 15x to the 2, right? And that's what you multiply to get the first term, plus a negative sine x, which is actually just minus sine x. And that would be the answer, right? So if you can't picture it, let's see if I can actually, I cannot. But let's see if I can insert a equation to show you how to do this. We'll do this one, and then so you can see it, right? Okay, because some people are giving me these really weird looks, and that always worries me. All right, that's not working. Let's kind of do something like over here where I add in one of those, and I'll bring it up. There we go. So let's make an equation, right? There we are. And I want to move this equation up here like this. There we go. Again, this is a neat little thing, right? Because I find it's really cool. So again, we want to say that the first part of the equation is, and this is what I would write down. I would say let u equal to sine x minus 5x to the 3, right? 5, the way again I would do the to the 3, x to the 3 is one of those, right? So I would say x to the 3, and that's what u is, right? So we can say that if that is u, then we can rewrite the equation as something like y. I'm probably going to have to insert again. We can say that then y is equal to, y is then equal to u, oops, let me just insert that stuff, is equal to u, I know it's hard to do this, right, to the 6, right? Do you see that? Y is equal to u to the 6. That's the new equation. That's like doing this, but we're letting u be sine x minus 5x to the 3, right? So we can also say then that if this is true, right, if this part is true, what I want to do now is find the derivative. What I want to say what y prime is, right? So let's insert another equation. So we'll reinsert one of these again. Again, I recommend this is far better than writing it by hand from a legibility perspective, but more difficult in terms of getting her done. So then y prime, we can say that is equal to, let's start with the outer equation first, which is 5, and then we're just going to put this in here, 5, and we're going to go u, right? So sorry, I was wrong, 6, I'll be okay, 6 u to the 5, there we go. So that makes sense. So if we take the derivative of this simple outer one is 6 u to the 5, right? Would you agree? And multiply by u prime, right? Multiply by u prime. Oops, we'll put that in there. Otherwise, we'll get some weird. By u prime, right? That's what we want to multiply by. We want to multiply by u prime. And we know what u is. That's the form. That's the outer form. And let's rewrite this now. Let's substitute, okay? Don't worry if you don't see it yet, but I'm hoping you'll see it afterwards, right? Because I want to do this one example and then move on to integrals because we have no time today. All right, so here's our next one. So where y prime, we can say y prime then is equal to 6, and we want to put in brackets the stuff that we're going to put up, right? So let's just put this in brackets, right? And we're going to say in brackets that we're going to take the original equation, 6x minus 5 x to the 3, right? X to the 3, right? We're going to multiply that, right, by to the 5. That's all we're doing now. This part, this whole thing here is just this part, right? By the way, I haven't added the cosec's yet. I'm still handling the first term, and then I'll add the cosec's afterwards, okay? Just to make it easier. Okay, so that's this part, we can say. Multiply by u prime. Well, what's u prime? If u is sine x minus 5x to the 3, then what's u prime? Well, u prime would be, right, cos x, right, minus 15 x to the 2. Let me just put that in there. X to the 2. I'll move this over in a second so you can see it, right? And that, my friends, is part of y prime. We're going to rewrite this a little bit differently and see if I can move it over in a second. Because we really didn't really capture what y is. Y is not just y u to the 6. It's also plus cos x. Let's add that part in next. This is how actually I would write it on a test. Like plus cos x. That's the original y, right? So we can say that y prime is equal to 6 u to the 5 u prime, right? Plus the derivative of cos x, which would be minus sine x, right? So we're going to take that and add that to the end, minus sine of x. Check. Now, you don't have to write it in terms of u's and anything else. You can still keep it in its original form if you feel comfortable doing so, right? So the answer could be 6 sine x minus 5x to the 3 to the 5, all to the 5, times cos x minus 15x to the squared minus sine x. Just go to that line, and I would be okay with that as well, right? But I would give you a mark for doing this, this part, right? Where you're saying let u is equal to sine x minus 5x3. All you're doing is you're assigning a variable for the inner term. So the inner part, the inner equation, you're just making let u is equal to this inner part here. All right, that's the first part. And then I'm rewriting y. I'm just rewriting this part here in terms of u. So I'm saying u to the 6th instead of sine x minus 5x3 to the 6th plus cos x. I'm rewriting it. That's the first part. Then for y prime, then I keep it in terms of u in the beginning, right? Where I say 6u to the 5 times u prime, right? Minus the derivative of cos x. Sorry, so it's plus, but the derivative of cos x is minus sine x. A negative and a plus, that kind of cancels out to be a negative, right? Negative sine x, right? And then what I do is I substitute. The next step is substitution, where I say something like y prime is equal to 6, and we substitute sine x minus 5x to the 3 because that's what we've let u be. We're saying u here, and here's u. We take u and substitute it in here, right? And then we take u prime, so we take this sine x minus 5x to the 3 and get the derivative of this, which is sine x is cos x. That's the first term. And the second term is negative 15, because you take 3 times 5 is 15. X, 3 minus 1 is 2, so negative 15x squared. And then minus, again, the last term, which is minus sine x. Okay? Now, we'll do this more in lab, but this is the general form. Does anyone have a problem with this? Using u's. And I use this system more, especially when it's a more complex equation. If it's something that's easy that you can see, you know, when you first look at it, my intuition tells me I better take the derivative of the, I take the derivative of the outer multiplied by the derivative of the inner. That's really what the chain rule is all about. But sometimes the inner one is very challenging to see from the get-go. When you look at it, you're like, so what's the inner? Plus there's an extra term on the end? How do I do that, right? And what do I do first? So the first thing that I would do is get your variable. This part here would be the first part. So this is part 1. Let me see if I can kind of put it over to the side. And of course I cannot. Yeah, it wouldn't allow me to. But that's the answer to this first one. Okay. But this is the first step is doing this. Second is rewriting the equation. So that's mark. And if I made this out of 4 marks and all you did was do this part, I'd be okay. You get 4 marks. Right? If you showed me your work, like in the middle, I'd be okay with that too, because some people can just go right to the end. I know that there's people that can do that. When they look at it, they go, oh, it's the derivative of the outer times the derivative of the inner, and I'm good. Yeah.
I just want to double check. When you're given the derivative of like y prime, very simple. That's like what it is, right? It's y prime.
Y prime is the derivative of y, right? Yeah. Yeah. All it is different notation.
Yeah,
so if y is the original, I love it. So if y is the original function, then y prime is the derivative of y. Yes.
Other than cos x and sin x, we're going to see any of the other ones.
Sorry?
There's nothing other than cos x and sin x.
If only. Let's take a look. I'll try not to. How about that? I'll try not to. All right. So here's the idea here where, again, some more ideas. I just want to point out, guys, I can't compete with you. I really can't. If people have chatter, I just, you know, there's only me and there's a bunch of you. You're going to override me. So please, guys in the back, I can hear you really clearly, really, really clear. So just, I'm sorry, but this is how it is. And you're going to be picked up here on the mic too. So if you look at this, a few more examples, and this is not something for us to figure out, but think about where u is. U in this A, in example A would be the 2x. U in example B would be the x minus 1. That's the inner equation, right? And u in terms of the last one would be the 3x, because it's the tan is the function, and the inner part is u. Yes?
So why wouldn't you use the product rule for C? What's different about it?
Because you can't do, tan by itself doesn't do anything. Tan isn't there's product rule we use when we have 2 different equations or 2 different functions. We multiply them together. Here we only have 1 function, right? We have 1 function on the outside and we have a function on the inside. That's different than the product rule. But I like your thinking. You looked at it and you're like, tan, wow, if I multiply tan, I can do the derivative of tan times, using the product rule of 3x. No, that's not, it doesn't work, because tan must have an input. If you think about a method, right, tan requires a parameter, and the parameter is 3x, right? If you see that. All right, let's move on. I know there's gonna be other questions in lab. Please save them. Here's some examples. Again, I've given some other examples. So here's another really funky one. Okay, so I'm gonna ask Corey today. Corey, because Corey, you're the man. Tell me how I would solve this one. What approach would you take? So you see, it's a little bit different in this one, right? It's still the chain rule, right? But which one is u? What would you say u is?
The 2 to the x is replaced by u, then to the 5th, I believe.
Yes. So what you'd say is then, we know in this particular case, if we could think about u as being x to the 5th, think about this, x to the 5th represents u, right? Then if we were going to find the answer to 2x to the 5th, we would take u, pass it to the front, just like we normally do if we use the power rule, multiply it by, right? And it would be u minus 1, whatever minus 1 would be. How do I take x to the 5 minus 1, right? Well, I'd have to take the derivative of that. That would be the way we do it, right? So I take the derivative of that and then multiply it by the whole first term. And x to the 5, the derivative of x to the 5 would be 5x to the 4. So I would say if u would be x to the 5, I would say x to the 5 in front of the 2. That's what it would look like, right? And then I would say x to the 5 minus 1, because that's what we do with the power rule. We subtract 1 from it, right? That would be the top part, right? And then I would take to multiply by 5x to the 4, and that would be your final. You guys can see that, right? Did you get the same result? Okay, good. How about this bottom one? Now, this is a little bit more tricky, right? The bottom one, the reason why it's tricky is because there's a couple things happening here, right? If y is equal to this inner part, and I want to do this, I got some other pieces. First, I need to use the quotient rule, right, to figure this out. Now, which one do you do first, the quotient rule, or do you do this other u thing, right? That's where students get really, messed up about. The answer is it doesn't really matter, right? I would probably do the quotient rule first, and when it comes to that term, which term am I talking about that needs the chain rule? Not all of it does. Which term needs the chain rule? Sorry? The bottom one, sine squared x. That is something that needs the chain rule. You can use the chain rule there. How about this? You could also look at, and this is kind of funny, you can use the chain rule here twice, right? If you think that 5x to the minus 2 is u, right? If you looked at that as u, then it's like saying it's u over sine squared x plus 10x. You could look at it that way as well, right? So there's a bunch of different ways to approach this one, and there's one answer. Now, am I going to give you something like this on a test? Probably not. Not this complex. Only because I don't want to kill you. I want to remember we're computer scientists. We're not necessarily mathematicians. But you may see one complex one, not like this, but another complex one. That if you do, there's no bonus. No. All right, we're gonna get more to chain rule. Oh yeah, maybe we'll do a bonus just because you're asking, right? We're gonna go more chain rule stuff. We have no time. We're sitting now in a point where I have to move on, and we have to talk integration in the next hour, right? In a bit, and I don't have a lot of time to talk integrals, right? And integrals is like what we did with derivatives, but in reverse, right? So it's like we've learned to drive the car forward with derivatives, and now we're learning to put the gear, in reverse and drive backwards, right? That's where we have to think about it, okay? So let's try this. So here's integrals for you. All right, so what we've been trying to figure out with derivatives is that we want to try and find the slope of the line, the tangent line to the curve. That's what derivatives really are. Or another way of talking about derivatives is the rate of change. That's what we want to find, right? And that's what we use derivatives for. But now we want to have this other thing happen where we want to find some simple stuff. For example, here's a simple question. If a car travels 60 kilometers an hour for 1 hour, how far does it go? Well, if you look at this as a graph, and we look at the time as the bottom part is the time, and the top part is in terms of distance. You can actually do it either way because it's 60 and 60, right? If I'm moving 60 kilometers an hour, this is the speed, here's the speed, and this is the time, right? Or this is the distance, 60 kilometers an hour for an hour. I actually do 60 kilometers, right? So because I'm moving 60 kilometers, that's the rate of change. See, the rate is right here, kilometers per hour. When you see something like that, one kind of unit in terms of another one, kilometers per hour. In your mind, you think rate of change. Here's the rate of change. How many kilometers am I traveling for every hour? Rate of change, right? Kilometers per hour. If I think about rate of change, I'm thinking, okay, well, this is kind of, I already got the velocity. Here's my velocity, 60 kilometers an hour. And now I want to somehow get to the position function, right? That's kind of what we're doing here. I'm saying, well, if I travel 60 kilometers an hour and multiply it by the number of hours, I'm actually traveling this far, right? It's actually displacing the car. I'm moving a certain point. So I'm actually talking about distance in some ways, aren't we? If I say, what's the distance? If you're moving it this fast, I'm actually saying, hey, get the integral or the antiderivative. How do I go back from velocity to distance using, how do I do that? Distance we can calculate using the position formula, right? Just like we talked about with the other way around. And here what we're doing is we're kind of going backwards. So here it's pretty simple. We just got this rectangle here that we can draw. And if I fill in this rectangle in the bottom, you can see that this area, right, is the distance. The area of the rectangle is, we want to find the area under the curve. To find the distance, we want to be able to find that it's 60 kilometers. But what happens when you have a question like this? If a car travels for 60 kilometers for the first 30 minutes, and then 70 kilometers for the second 30 minutes, or another 30 minutes, now how far does it go? Well, we know that if it travels 60 kilometers for 30 minutes, how far did it go in 30 minutes? Right? 60 kilometers for 30 minutes. 60 kilometers, if I'm traveling 60 kilometers an hour for 30 minutes, per hour is 60 minutes. That means I'm only going 0.5. I multiply 0.5, right, times 60. That means I'm only going to move 30 kilometers. Here's 30 kilometers, this part. And then I'm going to switch my speed somehow, really drastically. There's no gradual thing. All of a sudden, suddenly I switch to 70 kilometers an hour immediately. Doesn't really happen in real life. There's some kind of acceleration. But let's suppose there's no acceleration and zoom, I'm just teleported to 70 kilometers an hour, right? Which isn't like real life. And I go 70 kilometers an hour for another 30 minutes. Well, then I'm going to get half of an hour. I'm only going half of an hour. I'm doing it per hour. That's the unit. I take half an hour and I multiply it by, or 30 minutes, half an hour, I multiply it by 70 kilometers, which is 35. So you take the first rectangle, which is here. This is the area under the curve, plus the second rectangle here, and you add them together. And then you have the answer, right? You have 30 for the first part, the first half hour, plus 35 for the second half hour. So to give you a total of 65 kilometers, if you change your speed halfway through, somehow, immediately, right? Without any kind of acceleration. Do you see that? So this is great when it comes to real linear kind of speed changes. But what if, and this is where it gets kind of crazy, what if you have an area under the curve like this? What the heck do you do now, right? And this is where you kind of have to think about it. Can I develop a method where I can use the idea of rectangles over and over again to approximate the area under the curve, right, as much as possible? Because that's our tool, right? Rectangles and triangles, really, at the end of the day, right? So can I use rectangles and maybe triangles to approximate the area under the curve as much as possible? And I'm going to have to use multiple rectangles to do this in different steps, right? Which is going to kind of look like, see if I have the actual thing down here. Some kind of look like this, right? When you kind of have this thing here, right, where I have a bunch of rectangles to try and estimate the area under the curve. And if I add the areas of all the rectangles together, then I have an approximate area under the curve. Now, of course, what I want to do is I want to get more rectangles and more tiny slices. This is part of integration, right? And I want to integrate them together. Here are my terms, right? So I get all these rectangles, little tiny slices of rectangles all throughout the entire graph here, smaller than these ones, obviously, right? So they're more accurate. And so I can get an approximate area under the curve. And that, my friends, is called integration. How do I get the exact area, though? Because this is an approximate. It's not really real because the curve is wild, right? We got some crazy equation on the curve. How the heck do I do that, right? So imagine this, if this was the position function that kind of went like this. So it kind of speaks to velocity changes, right? Velocity changes because my position changes, right? Kind of weird. So some kind of velocity changes throughout my journey. and I want to know the total trip length or trip distance, right? And it's some weird function with acceleration and some kind of, in places, deceleration. So I accelerate here, decelerate here, accelerate here, or my velocity changes, changing velocity, but continuously overall increasing my velocity and my distance. How do I do that, right? Well, we just do the antiderivative, because we want to go from velocity, if I have a velocity, or even acceleration, back up to position. And then we can find the total area under the curve, so to speak, or the total, we can define the position function to kind of discern our approximate or exact distance. Does anyone see that? So a lot of little rectangles, that's our tools, right? And back in the day when they first developed calculus, that's what they did. They said, like, how can I, if I'm a primitive mathematician, and I'm trying to figure out, how do I figure this out? I'm going to try and take tiny slices and cut them out and put them in there and add them all together so I can figure out approximately the area under the curve. So again, can I use 2 rectangles or 5 rectangles? How do I figure this x squared? And if you remember, I talked about a function, a graphing tool that I recommend called Desmos, right? It's free to use. So here's x to the 2, right? Here's x to the 2. And I want to be able to find the area under the curve here, right? Between, let's say, x is equal to 0 to x is equal to 2, to this little interval here, right? How do I find the area under the curve? If you notice, there's like little triangles. There's one, there's a rectangle right here, and there's part of a rectangle here, and there's part of a rectangle, but guess what? There's a part of it that's kind of outside the curve, not really accurate. And there's another one here. Maybe I could make a smaller, cut as I go closer. You can see that there's smaller rectangles. And maybe you can even actually add up the squares if you think about it, right? It's another way of doing it, because squares are just another type of rectangle, right? A perfect rectangle, that's what it is, right? Then if I keep going closer, you can see that it's slowly, you're going to have the ability to really approximate closer to what the area under the curve is between 0 and 2, with all these little squares counting as areas, right? Would you agree? I want you to understand this, because if you don't get this, then you don't understand why we want to do integration in the first place, right? All right, so remember before we had position and we wanted to get velocity. Now we don't have the position function, and we want to get the position function from velocity. We already have a velocity, right? A velocity function, and we want to get the position function. How do we do that? So it's the idea of taking the sums under the triangle, or the curve, which we call Riemann sums. Riemann sums. Now, do I need you to remember that on a test? No. All right. But so that you've heard the term before, this idea of Riemann sums, and there's a bunch of other stuff. If you actually delve deep into calculus, which we're not going to do, we're not going to delve deep into calculus. You can actually look at the Riemann methods of doing certain things, of approximating the area under a curve, which we're not going to get there. And we're not, see this like crazy equation. When you look at this first equation, you're like, what the heck is that? Whenever you see the Z, this big capital Z, what does that stand for? Sum of, that's what it means of, from I is equal to 1 to N, right? When we start at 1, all the sum of all values from 1 to N, when N is infinite, right? Because N, we're finding the limit as N approaches infinity from I is equal to 1. We're starting at 1. Hey, I'm almost doing a for loop here, right? For I is equal to 1, right? Where I is less than infinity, increment. That's what I'm doing here, right?
Under a curve.
Right? Area under a curve, right? And then what we're doing is we're taking the area, and we're kind of getting the antiderivative, and that's what this part is here. And we'll talk about that down here. Okay, let's continue going down. So that's what we talk about Riemann sums. We need to use antiderivatives, and there's two types of integrals, the indefinite integral, right, and the definite integral, okay? We're going to talk antiderivatives and indefinite integrals first, and then we're going to move into definite integrals later, okay? I'm just giving my time a check to see if we're covering everything. So here's an example. So we now have, I'm just going to pull this up so you can see this. We've given a function, its derivative will give us the function's rate of change. That's what the derivative does. We want to find the other way around. We want to find, how do I get, how do I do the antiderivative? And really what I'm doing is I'm going to calculate the antiderivative by looking at the derivative figuring out how I got there, and adding c to the end, where c is some constant. Why can I not figure out what c is in an indefinite antiderivative or indefinite integral, so to speak? Why? Because if I have some equation 4x plus 5, let's suppose, let's map it out, okay? Just to give you a sense of what we're doing here. Oops, no, I don't want to bring Visual Studio Code into play. Let's suppose that my equation, my final equation, was some 5x to the 2, right, plus 3. That's my equation. So somehow my final equation, or we'll say that the y prime, that's why it's not mapping it, my y prime equation, right here it is, here's 5x to the 2 plus 3. That is this equation defines my velocity, right? And I want to get the position equation. Okay, well, how the heck did I get 5x squared, first of all, as a derivative? What did I do to get here? It was something times something, right, to give me 5. Woo, how the hell did I do that? Let's make it a little easier, right, because I don't want to kill you guys. So let's say this was a 6, okay? Could you figure it out now? What would be my original, if I looked at the derivative, right? It would be, what would it be? Come on, guys. 2x to the 3, someone's shouting out. Let's write that down as another equation, right? So I'm going 2x to the 3. Here's 2x to the 3, right? And what about the last part? Plus 3x. Okay, what about the last part? There's another term that's missing, which we don't know. That's the c, some constant. You can plug in whatever you want afterwards, but we don't know what c is. So it actually would be plus c, which we can't map. And I could add a slider for c. Here's c, where c could be different values, right? And all it would do is move our equation one way or the other. We don't know what c is, right? But the great thing is if c was a positive value, like let's say 2, then this would be your equation, right? And this is what we're looking at here, right? And especially if x was time, that's let's say this is your position function. Let's say this is, and where you want to kind of put in the idea that x, actually we just don't need that. We can say that where x must be greater than 0, or greater than or equal to 0. Let's see if I can get that in there too, just to give you an idea here, right? Here's where x is greater than 0, so we don't need that one. And same thing here. We don't care about the values of x that are less than 0. Why wouldn't we care? Because time is positive, right? Time is positive. So there's the equations. Let's move this down again so you can see. You can see that if they track pretty closely, don't they? Here's the original equation, or the one we have for velocity. Let's say this was velocity, the red equation. And then you can see that the position equation tracks pretty comparably to the velocity equation, where c is 2. Right? But what if c was 5 or something crazy? You can see now that it would be a bunch of different kinds of equations. In fact, what we're getting is a set of equations where c can be any number, right? Any number. Because that's what c is. C is some constant. So it could be a negative value, it could be a positive value, and it would give you a set of equations that would be the solution, right? This is called the indefinite integral. We do not know what c is, therefore it's indefinite, right? Okay, let's take it one step further. So if this, in fact, instead of this being the velocity, instead of the red line being the velocity, let's suppose, follow me here, that the red line was actually acceleration. Let's say this is the acceleration function, right? And we found the antiderivative to find velocity, which would be this one. Now I want to find the antiderivative of the antiderivative, right? So I can find position. You see that the second antiderivative was what we say, right? So let's add that in an expression down here. We'll pull it down here so we can see it down over here. Now, how do I find the antiderivative of this equation when I also have some c in here, some constant value? What do? How do I write that down? Can anyone think about it? Finding the second antiderivative. Come on, help me out here, guys. So what value do I multiply to get 2 if I have 3 up top? So something multiplied by something is equal to 2. Something 3 multiplied by something is equal to 2. What do I do? How do I do that? 2/3. That's interesting. Take a look at that. Is that 2/3? Would it be 2/3? Anyone else? Half x. So something to the 4, definitely. It's got to be something to the 4. So something 4 multiplied by something to get 2, right? Which means it's got to be x over 2. Yeah. Think about this, right? Because we know that we're going to get x to the 4. X to the 4 at the end. Because remember, x to the 4 becomes, 3x. It's going to be 3x to the 4. So, sorry. X to the 4 is going to be something 4x to the 3, right? But we don't have 4x to the 3. We have 2x to the 3. That means somehow the original term got halved, which means this one must be 1 over 2, right? You see that? In order for us to get this, we took 4, multiplied it by this. 4 times 1/2 is 2 to the 3, or 2x to the 3. That's how we got this one. And look, we almost kind of got the numbers here, right? That's how we figure out the first one. Next, now about the 3x. What do we do with the 3x? Something times, to get to the 3x, we know that this term would be something x, right? We got to the 3, but it's going to be x squared, right? Something x squared, and we're going to get 3 when we multiply it by 2. What number do you multiply by? What was that? 3 over 2? Okay, so let's see that. So if I take 2 times 3 is 6 over 3 over 2 is 3, right? So let's do that. So we'll say 3 over 2. Do you see any correlation? Here's 3, and here's 2, right? Here's 3, right? Or here's 2, and here's 4. Here's 2, and here's 4. Here's 3, and here's 2.
What are you trying to make there?
Right? It's almost like I'm taking the original value that's in front of this is the way I'm doing it, in front of the x, right? And taking it over my current exponent and multiplying it by what I have to get the answer. So example, if I take 3 over 2 times x to the 2, and if I take the derivative of this, then I'll get 3x, right? If I take 2 over 4, which is 1/2, multiplying it by x to the 3, that'll be the derivative. So I'll get 1/2 is the answer, right? Now you don't see yet. What about this one? What about the next term? What do I do with the c? Anyone know what to do? Cx, right? Because it's going to be in terms of time. I'm going plus cx. So I already have a value of c. This is going to change. Am I done? No, I need another constant, right? Some other constant value, because I'm going to the second antiderivative, right? So let's say we'll call it d, and where d is another slider, some other constant, right? So therefore, I could have a series of functions. Let's just make d as 1 for now, and let's just use c. We can see that it'll rotate all the functions together, right? It'll change or translate these functions depending on what c is. Let's leave it c as 4, let's say. In this particular case, that's one solution. And here's another solution, right? Where d is some other kind of value where I can move around the position function. So in this case, these 3 functions, orange would be the position function, blue would be the velocity function, and red would be the acceleration function. And all we're doing is we're moving backwards up the chain to get from acceleration back up to position. Do you see that in what we call antiderivatives? Some of you are falling asleep because you guys are bored to crap, right? Yeah.
I just had a question in regards to the d. Does that one not have to be greater than 0 then, considering c?
Yeah, we definitely have to make. Sorry, you're right. That definitely has to be greater than 0, but just like everything else, because if d, if we're talking in terms of time, then where x is greater than or equal to 0, we definitely do that, because in this case we're talking about motion, right? Yeah. And since motion is, in our world, only moves in positive increments of time, right? Unless we want to do some kind of we want to do regressive motion to find out what, if I go back a step, back a frame, if I was going to do it in terms of gameplay, if I could calculate the previous frame, then I would be going a negative time value, right? But typically we want to go forward frames. We want to look at the next frame, the next frame, the next frame, right? So in the next frame, and some people ask me, well, what the heck does this have to do with gaming? Well, if you think about it, if I want to calculate the velocity every frame separately from the position function, I have some alien movement. Here's the alien movement, or some kind of slope of motion, right? And I want to find the velocity every frame from the position function. It's the derivative, because I've got the position function and I want to find the rate of change of velocity. But if I already have the velocity, let's say, for example, someone gives you a velocity function, and I want to find the position function based on the velocity function, then it opens up a series of other functions that I could find, right? Now, typically what we normally do is we don't use indefinite integrals to define a, the position function or the velocity or even the acceleration. We have definite integrals. And what I mean by that is we have a range. I've given you a range. I want to know for example, the velocity between time 0 and time 5 in terms of where time is equal to seconds. Time is seconds. That is a definite integral. I've just given you c, right? I've said that c, right, is 0 to 5, something like that. I've given you the integral, and I don't have to. I can remove c because c becomes irrelevant afterwards, right? All I care about is time is equal to 0 to time is equal to 5, and I want to find the difference between those two values, and that's what d and d in this particular case is 0.1. Let's make it a 1. I can probably type it in as well. There we go. There's 1. All right. Let's keep going. So this is what the antiderivative is. It lets us find whatever the derivative was, right? The original function f plus c. That's the indefinite integral. Okay, because we don't know what c is. C could be a number of values, right? So it opens up a set of equations that match that potential. There's all kinds of things, right? But typically, what c will do is just shift my graph, just like you saw. It'll shift the curve one way or the other, depending on the values of c. Okay, let's keep going. All right, so now we're going into some examples. So let's find the antiderivative of 16x to the 7 plus 4x. What would you do first? Come on, guys. This is something where you can't sleep. You need to kind of try it out with your pencil and paper. We're going to do more of this in lab. But how would you approach this problem? What's the first thing that you would do? What would you do first? Okay, you could think about it, but let's start doing it together. Let's write it out. So I'm going to kind of go in here. And again, I'm going to kind of make a shape. So I'm going to kind of put in my equation. Let's do one of them, and let's see how we can figure this out. So I'm going to go into my equation here. So I want to do an equation. There we go. And I'm going to move this equation just underneath here like this. And let's see if I can figure out the derivative, what f is. So if f prime at x is 16x to the 7 plus 4x, then what is f? What's f of x? That's what I'm going to ask you, right? What is f of x? Find the antiderivative. So I'm going to write down the antiderivative in terms like this. Then f of x, if we know that f prime at x is equal to this, then f of x, which is the original function, we're going backwards, right, is equal to some value x to the 6, right? Or, sorry, x to the 8. Let's try that out first. Let's go one the other way around. X to the 8, right? We know that it's going to be x to the 8. So what value do I multiply 8 by to get 16? Yay! Someone figured it out. So 2 times 8 is 16. So that satisfies this part. And then plus, what's the next part? Well, no, we need to do the next one. I like your thinking, but it won't be plus 4. It'll be plus x to the 2. We put the x to the 2 next, right? Actually, I messed up here. Hold on a second. I want to put another value. Some plus some x to the 2. Just bear with me while I fix this, because x becomes x to the 2, right? And I add a plus in there. So something that you multiply 2 by to get 4, 2. Yay! Wow, that's really hard, right? And then, am I done? No, because we don't know. It could be anything that we got because some constant becomes 0, right? We don't know any constant we put in there. When you take the derivative of a constant, any constant from 0 to infinity, right? It still becomes 0, right? Actually, from negative infinity to positive infinity is still 0, right? So we say some c, and we write it in c, capital C, because c is a constant. And that would be the antiderivative, the first antiderivative, we'll say, of f prime at x. Yes.
Right. So what you're suggesting for us to do in questions like this.
See how I wrote it? What did I write?
You know, but like how to do.
Yes, go on.
Step 1, step 2,
Yeah.
step 3 kind of thing.
Yeah.
Would be whatever the exponent from the derivative one is would become the antiderivative. Like so if it's like x to the 7, it would become 8, and then do that.
Yeah, because the power rule.
Coefficient that will.
Yes, because the power rule then, Corey, would be like this, right? If using the power rule, I got something 16x to the 7, because that makes sense. I would use the power rule to get that one, first part. The first term, definitely I use the power rule. The power rule says that I take n, the exponent, I multiply it by the first term, x, right? And then I take n minus 1. So in this case, I would say n plus 1. So I take 7 plus 1, 8, right? And then, okay, so it would have been 8 that I multiply by some value to get 16, right? How do I get that next part, right? Now, this is another way of thinking about it, right? Think about 8 and think about 16. If I took 16 over 8, what value would I get in front of the x? 16 divided by 8, 2. It's almost better to write it that way. In fact, I could write this, I could have written this in terms of, instead of 2, I could have written 16 over the 8 times x to the 8, right? And then I could simplify that, 16 over 8 is just 2, right? Why am I saying that? Because it works for everything if you do it that way. All right? So I take the original, whatever I have in the derivative, 16, multiply by n plus 1, right? Or divide it by n plus 1. So I take the original 1, 16, the first part of the term, or the coefficient, like Corey was saying. I take the first coefficient, 16, and I multiply it by n plus 1. So in this case, the exponent n would be 7, plus 1 is 8, and I divide it by that. So 16 divided by 8 is 2. And then I get my n plus 1 term, and I put it into the antiderivative, x to the 8. So that's what it would be, right? Now look at the same thing here for 4, right? I take my new term, so n plus 1, n is 1, 1 plus 1 is 2. I take 4 divided by 2, and I get 2. And then multiply it by this, and now I get 2x to the 2. But much easier to figure out than if you're trying to figure it out in your head intuitively, right? Let's do another one. Let's do another one, okay? So I'm going to just take this one, and we'll do another one, okay? Let's do the second one, all right? Let's see if you can do this. So no, let's not do the second derivative yet. Okay, second derivative is more difficult. I just want to focus on basics, okay? Without scaring you away. All right, so we have x to the 3. What is the antiderivative of x to the 3? Well, we know it's going to be x to the 4, right? Something x to the 4. So let's write that in. So we're going to go equation, right? We're going to go x to the 4, right? So we're going to sum x to the 4. There we go. We know this part is true, 4, right? Uh-oh, we have 0x to the 3, right? So 0 over 4, right? Is it 1 or 0? 1, right? I have 1 over 4. That's what I would write in here. Let's see if that's true. If I followed my logic, right? It's like 1 over 4 x to the 4. Is that true? I'm not done yet. Plus c, right? I need to write that last part in, because if I don't write plus c in, I haven't finished up my equation. I need to write the plus c because it's an indefinite integral. Yes?
What if for your final answer you forget C?
You lose a mark or half a mark. I'll take a half a mark off. Because you know what? In this particular case, you need to put the c in because it's indefinite integrals that I'm asking for, right? You're going to see another notation for this, okay? Another notation for this altogether. You might see this equation written, and I'm going to talk about it later on, with this funny shape. It looks like a weird L, right? Or a weird S, right? It kind of starts at the top, a really funny S that goes down, a really long S, and then you're going to get the equation, let's say 16x to the 7 plus 4x, dx. You're going to have that at the end, right? And I want to say, find the integral of this equation. And when you see it just like that with this big S, you know in your mind, if it's all it has is the big S, it's indefinite, okay? If you see values at the top of the S and the bottom of the S, that's definite. And we'll show you the difference between definite integrals and indefinite integrals in a second. I'm not going to do these ones. We're going to do them in class. And let's see what kind of time frame I got. I'm just going to save this so I can see that I've saved my, I can't save it. I can't save this yet. Cancel. Just from a time perspective, we're sitting at 4:43. I think it's good to take 5 minutes to get some washroom break going on. And then when we come back, I will do the definite integrals and talk about how to figure those out. Okay? Let's take 5 minutes, guys.
The only